So as I said, I'm Steve, and this is Greg and Nick as well, and we all work in Android, and we're here to tell you today about what we've been doing with Android and LLVM over the past several years. I have the first part of the talk to talk about basically userland and how that sort of progressed, because that was the first part of the project that we undertook. And then Greg and Nick are going to talk about some kernel aspects of this and talk about how we're actually using LLVM in Android. So, and I do want to point out, this is a huge effort by a lot of different people. I don't have a specific thank you slide for everybody in here, but the entire LLVM community, our partners, vendors, other teams at Google, everyone has done such an amazing job to help bring this actually to fruition within Android. So it's not just the three of us, it is actually a giant community effort. So first thing, like we'll talk about this, I have a bit more stories to my part of the presentation. We started out, if you're trying to make a large change in an organization like switching compilers, this is pretty hard to do. You can say, oh, we're definitely going to switch compilers, but it's very hard to back that up, especially if upper management is sort of questioning whether or not that's worthwhile to do. So we sort of built this up piece by piece over the years. Our initial Clang LLVM work really wasn't to replace GCC. We were just using it to facilitate some on-device compilation. We'll talk about that. And eventually, a small group of people realized, hey, this is actually more important than just the small pieces that we're using. We should actually look at doing more and more. And so we started growing and growing and growing, and we built this. And we got partners on board, we got vendors on board, we got other teams on board, we got the whole entire LLVM community helping review code, fix bugs, and rely on them for some advice for some of this. But eventually the end goal was clear. And so this is a few years ago, and it said, it's time to have just one compiler for Android, one that can help find and mitigate security problems. This was a huge statement, and this was actually the thing that finally sort of like gave us full support for doing what we were doing. So lesson one is really to grow your support. It doesn't make a whole lot of sense to try and decree these things. If you start out small, you can actually, sort of build up to the large change that you want. So I was talking a little bit about the brief history. I have another history slide after we go through the real meat of my part of the talk. But the initial part of this starts with a project called RenderScript. I gave a talk about this several years ago. This was something that was using LLVM bitcode as a portable IR, something that everyone here knows is downright the wrong thing to do. We were warned repeatedly not to do this. We did it anyway. It wasn't the greatest rationale for having done it, but it did serve its purpose at the time. And this was basically doing bitcode JIT on the device, and it's still there today. So we were just basically using LLVM on the device, and we were using Clang off the device to actually create the bitcode. So it wasn't really doing a lot of other host compilation. It was really just there for this parallel compute thing. But we loved bootstrapping at the time. We made everybody suffer through LLVM compiles in addition to all their Android compiles. So this was back in 2010, end of 2010 actually. By March of 2012, this little local Clang thing appeared. And really this was so that we could actually turn on Clang for some of the other parts of Android that we're building. So this was a way of just saying like, hey, let's build this particular component with LLVM because we're going to get some extra benefit out of it. And the main use for this was starting to use address sanitizer on critical libraries. And also libpng and OpenSSL wanted to do things like ftrapv so that they can trap on overflow. This was before we were able to bring ubsan and stuff like that to Android. Of course, local Clang sort of snowballed a little bit as we encountered other ABI issues in Android, and we said, oh, well, we should probably start using Clang a little bit more. So this sort of grew the footprint of Clang for Android at the time. In April of 2014, while I was actually out on leave, Clang for the platform became not equal to LLVM on the device. And this was basically a part where we started splitting this apart and said that on-device JIT is going to do one thing, but we don't want it to hold back other Clang updates. So this was that kind of a turning point where it's like, no, we're serious about using Clang for other things other than just on-device JIT. And by July 2014, host builds, and this is really talking about the tools that are used to build Android, were being built with Clang. All of them were being built with Clang. So this is things like stuff for packaging up Android apps and some of the other compiler stuff that appeared for Android was now going to use Clang. So as I mentioned, this slide was animated before, but now I'm on a PDF. So local Clang was a flag that we had for the Android build system. If it was set to true, we used Clang for the module. If it wasn't defined, we used the default regular compiler, which was GCC. That was the only thing we had at the time. It seems, pretty obvious. And then we said, well, you know what? Maybe we want the ability to set this to false so that we can actually use GCC to compile this module. And we were sort of thinking ahead to, well, what if we want to default to Clang? What if we need, the ability to turn it off real fast? So this goes to my, so local Clang equals false sort of, came up with the, well, we might need to do some GCC specific thing. In particular, testing our libc, which has to work for both compilers because we have native tools users that are going to use both. Some tests were also a little dependent on GCC implementation details, and we didn't have time to rewrite a lot of those. So we said, fine, we're just going to go ahead and bail out on those cases. And in other cases, we really didn't know how to fix some of these bugs. There were a ton of very, very weird and interesting bugs, and we'll cover a few of those. But it's really interesting, all of the different variety of things that you see. And you're like, if you don't have some way of, working past this, you just get stuck forever and spend a lot of time on these horrible problems. So this comes to my second point, which is that escape hatch is vital in any large project. You want some way to actually say, look, we're going to, use the existing thing that we know works, right? And so we designed this in a way so that we could actually just bail out conveniently for most of our builds. And I know I mentioned this before, and I sort of talked about this. If we had to turn off Clang, we wouldn't be here right now. We would still be fixing these hundreds and hundreds of bugs that we encountered. But instead, we were able to make progress in parallel. Every time we turned one of these things off, we filed a bug and we said, hey, so-and-so from your team, can you help us look at this? Can you help us understand if this is a bug in your code, if it's the compiler? We got people involved, right? And a lot of times, we would do the initial triage ourselves, and then we would sort of send this off to the other teams. But we didn't let it hold up our entire progress. And that was really the lesson from that. So I mentioned that we had a way to turn off set local Clang to false, because we then started experimenting with, well, what if we have a build that defaults to Clang, right? This seemed pretty logical and obvious. And so we actually did set up a separate build target like this. And you might say, well, why didn't you just try this in the first place? Well, we did the first time, and it was miserable. The device didn't boot. We actually had build breakages, so we were turning off component after component after component, because things just didn't build with Clang. It was like bug upon bug upon bug, errors everywhere. So at the point where we actually could turn off Clang for subcomponents, we said, hey, we can set up a second build that actually does use Clang as the default. And so one of the great examples where we actually had this side-by-side build, and we're using these things to look at two behaviors, was this AEABI functions for ARM devices. And so this was a bug that came up that was very interesting, and it manifested multiple different ways, but this is a great example. Please ignore the int for the size in this AEABI memcopy, because we all know that should not be assigned integer. It's pretty awful. But a lot of libraries notice that, hey, this function's sometimes not present in the libc. Well, in Android it is, but when you're building a lot of third-party software, they don't know that. So they just did the conservative thing and said, let's define our own. And they had to call memcopy, which is great, except for the fact that Clang decided that, well, when I see memcopy, I'm going to lower that to built-in memcopy. And for Android's target, that actually is AEABI memcopy. So you get a nice infinite loop, your stack explodes, your device doesn't boot, and everybody looks at each other confused. So we discovered this pretty early on, and then we discovered it again in another component later on, and then someone upgraded another component and we found it again. And each time we basically were like, local Clang equals false. We don't know why this is lowering the wrong way. We don't have the time to upstream the right proper patch. Let's just turn it off for now and we'll deal with it later. And of course, we eventually upstreamed the right patches that said, don't define this on Android. We have this function. Please don't, overwrite our version of it. So the next lesson is that the side-by-side build is great. So if you can actually, sort of do these comparisons, that's actually what's important, right? This is why, software development is a science, right? We want to be able to measure and compare things. And the side-by-side build gave us that capability. We did correctness testing, we had conformance testing, looked at code size, performance. I know everyone would love to see the numbers for this stuff. I'm telling you, it's super boring. There were some cases where performance was worse. We fixed most of that or explained why it was going to be worse. But essentially, this allowed us to get all the early regressions handled. So by making an actual official build, we actually were able to forward all the build breaks from this new build, once we got it set up, to everyone else. So when everyone wrote new code that tripped new Clang errors and warnings, they would get the build breakage message and it would say, hey, stop doing that. And they would fix their code, not realizing that, oh, why did my GCC build work, but your build didn't work, right? So we sort of, again, spread the work out amongst multiple people rather than just ourselves. So the next lesson is bugs happen. Sometimes it is the compiler. This is a few classic ones that we hit with assembly parsing. So this, again, was supposed to be a slow reveal, but now you can actually see it all. We have this great ambiguous expression here, which you would say, oh, operator precedence, we can figure out what this roughly does, right? Well, GCC and Clang don't agree. And of course, there's no rules for assembly for assemblers, right? Sometimes the order of the arguments is different, right? On different architectures and different assembly code that people have. So this ambiguity was directly in Bionic, our libc implementation, and it was terrible. And it was like, whose bug is this, right? They were like, GCC has been doing this right for years. Why would Clang do something different? And we said, well, look at the order of operations. This is kind of weird. And shouldn't you actually write your code to be clear for the people reading it? Like, this is not the obvious reading of that code when I look at it, right, as a developer. So we went ahead and cleaned these up. It's, of course, you know, both groups' faults. Undefined behavior is another great category, right, that we hit throughout all this Android LLVM transition. Signed integer overflow is a classic favorite. FWrapV can be used, has performance penalties, but we had plenty of people who said, we don't want to fix our signed integer overflow bugs. We'd rather use FWrapV. So we said, okay, fine, you can use that for now. Hopefully try and get most of them to actually fix their bugs in the future with UVSAN. Non-null was another case. So this is a particular nasty instance. Binder is an IPC mechanism on Android that's used all over the place. And it had this great method called asBinder. And the problem was it looked at this pointer and said, if this is non-null, go ahead and convert this to a binder object. And if not, just return null. Well, that seems pretty sketchy. And so, of course, when we switched to Clang, we were like, whoa, like we you know, Clang warned us and said, this is always non-null, so just go ahead and delete this. So we went ahead and deleted it. We didn't bother to actually try booting a device because we were like, this is brain dead. Who would do this? So, of course, the first time we get the test run, it says, all of your tests are failing. Why can't your device boot? And it's like, well, oh, there's a whole bunch of code where people are just shoving null pointers and calling asBinder on it because they didn't realize that that was not a thing they should be doing. So we had to go and clean up all of those. We had issues with memcopy, right? Assuming that the pointers are non-null. You basically see if one of the pointers is null, set the size to 0, go ahead and call memcopy just straight through. Yeah, well, Clang just removed the check for not source and not des because it said, hey, if you're calling memcopy, these have to be non-null. Let's just go ahead and eliminate that if check. So this is another pretty ugly one that we hit in multiple places. Inline assembly, again, we had some wrapper functions that were nicely written. They did some work on some incoming arguments to these functions. Then they went ahead and just did a branch to another function with the existing layout of registers and arguments that the calling function had. But they didn't bother to set any of the actual constraints. So Clang was like, oh, I see you're calling another function. Let me go ahead and help you out. And it would actually just go ahead and reuse some of those registers for interesting purposes and be like, well, you didn't say you're using R0, so I'm going to go ahead and use R0 for something else. And you would lose your first argument. So this was pretty awful. We had to go and fix a whole bunch of code for this again. The lesson here is really like, people are going to do what's needed to make their compiler and assembler happy, but they're going to just do barely that. They're never going to go and look into, did I really need another register in this clobber list? They're not going to notice that unless the compiler tells them so. Clang might tell you, but in general, the assembly parsers are not that, clever about it. So this was another interesting one. So ultimately, what do you have to have? You have to have a bunch of empathy for all these other teams because they're going to have these horrible bugs. They're going to have them all over the place. They're going to have undefined behavior. They're going to have all sorts of other tricky things where they did just enough to make the other compiler satisfied or whatever you're trying to do. And whatever big project you're actually working on is going to upset that balance. And the reason that you have to have lots of empathy for them is because you're going to need their empathy when it is your fault, right? There is nothing that makes developers more upset than when it actually is the compiler. You tell them it's not the compiler. The compiler is doing a fine job with your code, except for those cases where it isn't. And when they spot that, then they're like, oh, well, maybe next time it is the compiler. Maybe the time after that it's the compiler. And all of a sudden, you're triaging everyone's bugs just because they're afraid that the compiler did it to them. So you want their understanding when it is a compiler bug that, hey, you're going to have to insert this nasty workaround, but it's OK. It's just temporary. So the rest of the history, 2012, 2016, we basically covered that in those bugs. And now I go back in time a little bit. 2014 is when we mostly had the first side-by-side build of this working for Nexus 5. And it really had a lot of things turned off, but that's OK. By January 2016, we actually defaulted to Clang. So we switched our actual regular default to Clang rather than GCC, but we kept both builds running. There's still, again, a bunch of things that are setting local Clang to false. By April of that year, we actually got to 99%. We were literally down to like 3 projects. Valgrind was the last. It had a few really, really tricky, nasty issues. In August of 2016, we actually started forbidding people from adding new projects to set local Clang equals false because people would say, oh, here's a quick, convenient way to be productive. Let's just turn this off because I don't want to satisfy their warnings as well. And finally, by October 2016, so this is literally a year ago, we shipped the first 100% Clang userland on Google Pixel. So this was sort of a more or less quiet thing. Our team sort of knew about this, but it was, now we're basically a year later and still continuing that nice 100% userland. So some numbers. I did promise some numbers, I think. There's 597 Git projects in Android, and I calculated out all these lines of code last night. 37 million lines in just AOSP master. So this is not even all of our internal trees. So we actually have other internal code and vendor code, things that we can't share, that get built separately and checked in as a pre-built. We have 2 million lines of assembly. That's pretty disgusting. And that's not inline assembly. That's just regular assembly, right? So who knows what's going on. And about 25 million of these lines are actually in the external, like third-party projects. So these are things that are harder to migrate because you have to fix it in the upstream first, or at least hope that you're going to fix it in the upstream if you do insert a hack. So we had over 150 CLs to clean up errors that Clang uncovered. We only started counting this in like 2014. So this ignores years and years of work before this. Some were Clang bugs, some were user bugs, some were both. And we basically went about a 2-year schedule between making a final decision and actually shipping this. But in total, it was about 6 years, right? As I said, we started on doing LLVM work in 2010, and some of that was definitely helpful down the road. So, bonus item. If you need to deprecate something in a short time, I hope everyone can make use of this knowledge. And even if you can't use it, you can threaten people with it. It's great. So we had STLport, which is a runtime STL library that's pretty ancient and didn't have C++ 11 support and definitely wasn't going to get C++ 14 support and all these other things. And we said, hey, we're going to really want to deploy those things, so we need people to switch. We need people to get off of STLport. And the problem was we didn't control all their builds. And so there are all these unbundled apps where they were just using whatever was on the Android platform, so whatever libc++ or STLport that we had there, and they were just like, oh, STLport's there, I'm just going to keep linking against that. It's really hard to get people to change these things. And we said, no, you really have to change because we need the ability to upgrade things. So this is when one of the other brilliant people in Android said, I've got an idea. What about a sleep constructor? We control the STL. They only control their build of their app. So we went ahead in the middle of STLport and inserted a giant sleep 8 as a startup cost. So you want to start your app, you have now an 8-second penalty. And in the commit message for this, he also said, I'm going to go ahead and double this when I feel like it. So we checked this in internally in May of 2015. He doubled it in June. People noticed. And by August 2015, we just nuked the whole thing from orbit because no one was using STLport. So the next time you have something that you need to change, don't forget about sleeps. You'll also note there's a bunch of logging in here too to tell people what to do. It also makes for a great thing if you just log for their competitors in the log as well. So you can always say, don't use this app, use this other app instead. They're gonna want to fix that real fast too. So these are my takeaways. I don't want to take up any more of your time. Grow the support, escape hatches, side-by-side build. Bugs are gonna happen, and have that empathy for everyone else because you're gonna need it when your stuff is wrong too. We all know this. Compilers do have bugs. And when being nice fails, don't forget about sleep constructor. So with that, I'm going to turn it over to Greg.
Hi. I'm Greg Hackmann. I'm the tech lead of the Android kernel team. And I'm going to talk about our journey to get the Linux kernel building with LLVM and Clang. The best way to do this is to actually walk through sort of our history of our involvement with this, because as it turns out, not a lot happened for a while, and then all of a sudden everything sort of fell into place. So around 2014, when our compiler team approached us and said, hey, you know, LLVM is looking like the way forward for the platform potentially. Could you use this for Linux kernel? We basically decided, you know, once a year we would evaluate the state of building the kernel with LLVM. And we certainly did not start this project. There were a lot of external contributions to get the kernel partly building with LLVM. And a lot of this centralized around a project called LLVMLinux. It was hosted at the Linux Foundation. And so they provided basically a patch stack that consisted of two things. The first is that they had patches against what's called kbuild, which is the Linux kernel's build system. Some of that work had gotten upstream, so there was actually some skeletal support for instance, using Clang as an alternate compiler for some macros that had to know compiler-specific things. But not everything had been upstreamed. There was still a fairly large patch stack of kbuild changes that were out of tree and only available from LLVMLinux. It turns out that those changes were actually in fairly good shape. I don't know the context for why they weren't upstreamed, but we ended up sending them. They ended up getting upstream eventually in more or less a modified shape. There has to be some rebasing done. The bigger hurdle here was that there were a bunch of architecture-specific patches, because in every architecture there's basically kernel features that didn't build. And these were not, in many cases, these were not small features. And so these patches were labeled do not upstream. Or in Git conventions, you say signed off by on the commit to say, I wrote this, you know, I can submit this to Linux kernel. People signed off their commits and edited it so it said not signed off by, as a clear sign that you should not be sending this upstream. And these were things that were put in there to unblock building the kernel but not be able to boot them. So for instance, ARM prefetching on ARM64, totally disabled because at the time Clang couldn't deal with it. The one that really concerned me was there's a macro in the Linux kernel called read once, which is important for memory safety, which I don't know why, but Clang apparently could not process this in 2014. And so they redefined read once X as X and basically removed all the memory safety. So it would build, probably wouldn't boot. If it boot, it probably wouldn't run very long. That said, the fact that like so much of stuff was working even in skeletal form meant that we wanted to keep an eye on this. It just wasn't something we were interested in turning into a real end user product right now. So the annual check-in continued in 2016, and I'm going to be honest, I was still a little pessimistic. But what had happened over the past couple of years was that Clang and LLVM had continued maturing as a toolchain. And so the vast majority of those patches that we deemed unshippable just weren't needed anymore. And in fact, when we rebased the kbuild changes, we were able to get a kernel booting inside QEMU and a development board relatively quickly. That said, there were some significant issues. A lot of the stuff that had been sent upstream had bit rotted as the rest of the build system had evolved. You had to disable the crypto layers for hardware accelerated crypto on x86 and ARM64. In fact, the ARM64 crypto code crashes Clang. You had misaligned stacks on x86, so you got a lot of kernel panics. ARM64, it actually managed to panic before the kernel started, because the kernel ships code to work with EFI, and there was issues with some of the code that Clang emitted. And the one that we're going to go in a little bit later, and this amused me the most, was there's a core kernel module called Futex, which if you build it for ARM64, depending on the time of day and your kernel config options and the wind speed and direction, it might assemble or it might not. Nevertheless, we had workarounds for all of these things. Maybe not necessarily workarounds we could send upstream, but this was a sign that this is something that we're actually very close to having working. And coincidentally, we had several teams in Google that were interested in pushing this to completion. Besides the Android kernel team, the Chrome OS kernel team was interested in this, and we had other kernel teams in Google that basically came together and converged on this and said, okay, how can we improve both the kernel and LLVM to get these last little bits working? So before I go into the kind of thing we need to change, I want to talk about why the Linux kernel was so much different from a lot of other code bases. So it's a 23.2 million line of code base. So think of it as roughly the size of all the external projects in AOSP user space. And that code evolves simultaneously with GCC. What I mean by that is whenever a new version of GCC broke something, Linux went on GCC's bug tracker and complained. And they always added a workaround through a new command line flag or said, here's what you need to change or so forth. And so a lot of people felt like these two things were tangled together. You can't really build the kernel with anything other than GCC and maybe the Intel compiler. On top of that, the Linux kernel does a lot of things that most user space programs don't do. I won't go through all of these in detail, but just to highlight a few things. The Linux kernel it handles CPU exceptions, including memory faults. And so it actually knows what happens if you touch a bad pointer. And then there are a couple of cases where it actually depends on otherwise unsafe behavior doing something specific. We had a bunch of issues on x86 because depending on how you build the kernel, it may combine 16-bit, 32-bit, and 64-bit code into a single executable. Because some of this is used, for instance, to bootstrap at the very beginning when it's in real mode. Some of it is exported to user space where the apps may be 32-bit. And my favorite sort of confusing one is, well, the kernel's kind of an ELF executable in that you use an ELF toolchain, it has ELF relocations, but it's also kind of a COF executable because that's the executable standards used for EFI. And if you build for EFI, it will actually stick a COF header in front of the image and say, yep, I'm COF all right. And then it will run under the bootloader for a tiny amount of time until it actually jumps into the kernel. As far as the bootloader is concerned, Linux is a COF executable. It's also kind of neither of those things because it does its own dynamic linking. Basically, it's just sort of borrowing infrastructure from these two executables to the extent that it's necessary. That said, by the time that we started looking at this in 2016, the Linux kernel wasn't actually that unusual. So yes, Clang already builds lots and lots. Yes, the kernel does weird things, but Clang already builds lots of things that are in their own way weird. It builds compilers, it builds JITs, it builds web browsers. It even builds other operating system kernels. I know that it builds the FreeBSD kernel, and I would not be surprised if there are other kernels that are built with Clang. So yes, the Linux kernel is a little bit weird, as all kernels are, but the collective weirdness of all the things that have been compiled with Clang over time is really not that much different. And so there were relatively few corners of the C language that were left uncovered. On top of that, a lot of the really weird things I pointed out on the last slide aren't always meaningful in the C language. And so when Linux needs very precise semantics for things, it falls back on things like inline assembly, because that's the way it guarantees these semantics. It basically says, this is the exact code I want you to emit. In fact, by the time we had been looking at this in 2016, a lot of the bugs that we ran into were at the interface between C and inline assembly. And the result of this actually improved both code bases. So I'm going to give an example first of a case where the kernel was relying on undefined behavior. And this is a fairly complex macro with other nested stuff, so I won't expect you to parse it during the talk. But I will just walk through briefly what it does. So there's a macro that walks through a singly linked list. You basically at every step, it has a pointer to either something inside of a element on the list or to null. So what this macro does is if it's pointing inside of the struct, it just walks backwards some number of bytes that's known in compile time in order to find the start of the struct. But it also needs to know if that was null. So it then walks forward the same number of bytes, and if the result of those computations are equal to null, it terminates the loop. There's a small problem with this. So this assumes that pointer overflow and underflow by the same amount cancel each other out. And this is not defined behavior. In fact, it's not defined in such a way that the compiler can basically go, oh, this thing where you're comparing against null, I know that's impossible, so I'm going to delete your terminating condition. And so what happened was this macro was added to at one point early init on x86, and the kernel just went into an infinite loop because there was literally no way to terminate the loop. Clang optimized it out. And this is code that was introduced in August 2011. This is actually a fairly subtle bug because you're relying on undefined behavior that just happens GCC had never actually exploited before. Clang was the first compiler that had come along that exploited this. And so 6 years after this code was introduced, we finally had a fix for it. one of the members of the Chrome OS team said, okay, you basically want to treat the overflow and underflow semantics like this was an unsigned integer, so we'll just cast it to an appropriately sized unsigned integer, and then we get defined behavior. But in some cases, as Steven noted, it is actually a compiler bug. So here's the fewtext module that I talked about. So the fewtext module does something that's kind of interesting, which is it needs to know if a particular kernel API is available. It doesn't know this until runtime. And this is a potentially destructive operation because it does compare and exchange, as the name implies. So they don't want to pass in a valid pointer not knowing what will happen to it. So the kernel's approach is, well, we know that this API call does not trust its pointers. And so it actually turns off the part of the fault handle that it panics the kernel and traps the exception. And so if you pass in a bogus pointer, rather than the kernel panicking, it will just send back an error saying, give me a better pointer next time. And so this part of the fewtext module says, okay, we're going to deliberately pass in a null pointer knowing that it's going to fault. And we're going to see if it either told us that it faulted, or if it told us that this particular API call is non-functional on this system. So Clang had what would have been a very clever optimization, where it basically assigned that null pointer constant to a particular register that always reads 0. The problem is that you can't actually load from that register like it's a pointer. And so when you tried to build this kernel, this module, if everything aligned correctly, then it would emit this code with an invalid register assignment, and basically the assembler would say, I don't know what you're trying to do. This instruction doesn't exist. And this is actually a bug in the Clang ARM64 backend, where it basically the inline assembly routine said, I need you to treat this value like it's a pointer, and the register allocator neglected to know that if it's a null pointer, it cannot be used in this one special register. And this is an LLVM bug that has been fixed upstream. It's a case of the kernel doing something unusual and triggering behavior that just, it is technically a bug, but just has not been seen before. In order to trigger this, you have to be building for ARM64. You have to have inline assembly that loads from a memory address. And you have to have a caller that specifically passes in a null pointer constant just to see what happens. This is not something that most user space code is going to do, but in the case of the kernel, it does make some sense. So I will very briefly summarize where we are today. There's a very good longer form summary of this at an LKML link, which we have here. And I will sort of give a very brief version of that and a couple updates. So again, several teams within Google worked with upstream to contribute the kbuild fixes, mostly stuff that was out of tree in LLVMLinux and is now in tree in some modified form. We've contributed core architecture fixes to x86-64 and ARM64. And it's a little bit hard to estimate the size of these contributions because they were sent in over time. The best estimate I have is based on what we put in our 4.9 backport. So you're talking roughly tens of files changed, a few hundred lines, which is not bad when you're talking about a 20 million line of code base. There is still, unfortunately, one out-of-tree patch needed to build the kernel for ARM64. That is an LLVM bug. That is actually the thing where the crypto layer crashes, and we have a workaround for that, but it's not really upstreamable. So basically, once that gets fixed, the Linux kernel version 4.14 should be retroactively buildable for both x86 and ARM64. In addition, the Chrome OS team did backports to 4.4 and 4.9, which are the latest long-term stable releases. And those are available from Chromium in a Git repository that is mentioned in the LKML link. And I actually have a brief update to these slides. So we originally hosted these in special branches on AOSP. And just before I came up on stage, I got the notification that these had been merged into our main Android 4.4 and 4.9 kernels. So now don't check out those branches. They're not going to be updated. Just use the regular Android 4.4 and 4.9 kernels, and they should build with Clang. But all this is perfectly well and good, but we've been talking about can the kernel build, can it boot, can it run? But there's a gulf between it seems to work and we're confident enough that we're willing to ship this in production. With that in mind, I'd like to turn this over to Nick on the Pixel team.
Thanks, Greg. So Greg and I were just at Linux Plumbers Conference about a month ago in Los Angeles, and it was really nice. We got to meet some of the original LLVMLinux folks, and we had a blast talking with them and talking about how broken this or that could be, kind of thing. And so we were sitting with the lead on that, this guy, Ian Webster, he was like so thankful, and he was like, man, I'm so happy that you guys are like interested in this work and are picking it up and looking into it some more. Wouldn't it be great if we could ship an Android phone someday with a Linux kernel built with Clang? And I kind of looked at him and was like, yeah, wouldn't it be nice? So unfortunately at the time it wasn't announced, so I couldn't quite show it to him. But earlier this month we announced the Google Pixel 2 and Pixel 2 XL phones. And if you take one of these and plug it into your computer and you run ADB, and you take a look at the sysfs node,
It's blank.
You're kidding me, the GIF's not going to play? Of course. Okay, so no demo on this laptop. But if you take a look at the sysfs node, you'll actually see on the image that ships on day one that we are shipping a Clang-built kernel for this device. So we're using the 4.4 version of LTS for the kernel version, and the version string prints information about what compiler was used and the host machine and stuff. On day one, it'll ship with a kernel built with a version of LLVM 4, and then shortly later this year, we'll ship an upgrade where we're building with a 5.0 kernel, and hopefully another one soon with tip a tree, or however close we can get. So.
5.0 Clang, not 5.0 kernel.
Sorry, 5.0 Clang.
Yeah.
Yes.
Don't give anybody a hard time.
Time travel. So some of the benefits that we saw on the Pixel team is basically having one less tool chain to maintain between userspace and the kernel itself. For a long time, our team had just kind of been using a version of GCC 4.9, and a lot of people thought like upgrading or touching the compiler had a lot of taboo with it, that when compiler bugs were encountered, people didn't really want to be responsible for it. And I kind of did, so I was happy to kind of help out a little bit. And to me, LLVM is definitely beyond critical mass. If you see the sheer amount of contributors, of active contributors, over time and the number of companies contributing to it, it's clear that LLVM is here to stay. A lot of the work that I've been doing on the side is around static analysis and dynamic analysis, such as the use of runtime sanitizers. So Clang gives us all the tools that we need to be able to build these kind of tools ourselves. And while the runtime sanitizers are implemented both in GCC and Clang, they're developed first in Clang and LLVM. There's kernel variants, so while you might have ASAN in userspace, there's a KASAN, KUBSAN, KMSAN, KTSAN in the works. So one of the things that's really helpful, that's helped us find a lot of bugs, is being able to run KASAN and then be able to collect RAM dumps when we have kernel panics that we hit. But I would only recommend that for your truly dedicated dog fooders. Most people can't handle having too many kernel panics in a day before they get fed up dog fooding. Some of the benefits are additional compiler flag coverage. So we ended up doing side-by-side builds on Stephen's recommendation, and we'll see in another slide about pre-submit tests helped us out there, but I actually found real issues in the kernel. We're working on building more tools in the future, such as code flow integrity analysis, link time optimization, and profile guided optimization. This helped us shake out a lot of undefined behaviors in the kernel. Switching compilers isn't going to spot every instance of undefined behavior because two different compilers might wind up taking advantage of undefined behavior in the same fashion, but it can help shake out a significant amount. And the hope really was to kind of benefit both code bases. I think as Greg showed, both LLVM and the kernel have been able to improve kind of a cross-pollination. So we'll link to these slides later, but these are some of the bugs that in LLVM that we had found or ran into when building with the Linux kernel. Some new warnings that helped us out. So the ones in green here, had we upgraded to a newer version of GCC, we would have gotten for free, but the red ones, I believe, are unique to LLVM and to Clang. And one of the things that's useful is actually being able to have kind of both of these. And so one of the things I find interesting is like trying to figure out between compilers, what are the unique flags that they have and which ones do we find to be valuable kind of thing. I wish it was a little bit easier too. But kind of the gist of it now is can we compile a working Linux kernel? So it's yes, with some caveats. There's a world of difference between like, hey, it compiled, and then the first time you go to run it, and you get an infinite loop or kernel panic or whatever. Like a lot of work between those two. But Greg summarized, right, top of tree, 4.4, 4.9 LTS. The LTS branches are the Chromium and Android forks that we maintain the patch sets for. Besides being able to build a kernel, you need to be able to run it on actual hardware. So we've kind of validated our device-specific configurations. There's a very long tail of all these other kind of hardware configurations to test on. So I can't say like, yes, it will work for you today in your configuration. So not just the hardware, our specific hardware itself, but of those 23 million lines of code in the Linux kernel, you actually don't want to ship all of it. There's a lot of architecture-specific code that you don't need. Kbuild compiles out a lot of that code. And then further for us, the difference between Android on a Pixel phone is we know exactly what hardware we're going to be running on. So we actually turn off, to lower our attack surface, disable a lot of code in the Linux kernel, file systems we never plan on using, etc. Versus a standard Linux distribution that who knows what kind of hardware they're going to have to run on and what they'll have to support. So we've kind of guaranteed our configs are good to go. A big caveat is we can compile the kernel. There's still a lot more work ongoing to assemble and link the kernel. So one of the key patches that we have actually disables the use of the integrated assembler, and then we need to pass our target triple along so that when we defer to bin utils, we use the proper cross assembler and cross linker. And then we've kind of guaranteed support for ARM64 and x86-64, but there's more work going on for other architectures, and we're looking for help too. Some of the things that we did for testing on the Pixel side for the kernel, there's a difference between pre-submit and post-submit for tests. Is how long does a test take to run? If developers are trying to get a lot of work done, the longer the pre-submit tests take, the more they're prone to either ignore them or get fed up or bad things happen. So on pre-submit, we have compile and boot tests. We have distributed builds of the kernel, so they're done within probably a few minutes. So we compile the kernel both with Clang and GCC with -w all, -w error, make sure that there's no issues with either compilers. KASAN is important to build pre-submit just because it has additional requirements on stack depth that you can go through pretty quickly. I found a lot of issues with very large structs getting allocated on the stack, which is problematic for the kernel with very limited amount of stack space. So we want to make sure that doesn't break. And then we also run the Linux kernel's linter to make sure no patches are problematic. And then on post-submit, we do fuzzing of our kernels and also all different kinds of regression testing. So functionality regression testing, performance testing, and power testing as well. So if you wanted to try this today, what you could do is you could clone the Linux kernel, make local mod config is a make target that will take your current Linux distribution and generate a set of configs as if you were going to build a kernel that would work for your machine. And you invoke make and pass it the argument cc equals Clang. And that's good enough to get started. If you want to cross-compile, you need to set the environmental variables for your architecture and what your target triple is. And then further, some of the user space tools as well can be built with Clang using hostcc equals Clang. So some of the future work, Greg alluded to, there's a lot more work to be done upstream on kind of both sides, but we're very close. A lot more of the work for us is around the assembler and the linker itself. And then there's a lot of people who are kind of gated on this work who are pursuing really cool stuff at Google around control flow integrity, LTO, and PGO. We have a mailing list if you hit bugs in Android and let us know about them. And thank you so much for attending our talk today. We appreciate it. And I think we might have 5 minutes for questions.
Yeah, I don't know if the clock is accurate. I have no idea.
Hello. Yeah, thank you for a nice talk. Very interesting. Question. So when you switched to LLVM for different subcomponents, what kind of agreement you had with owners of these components? I mean, if something compiles cleanly, but doesn't work correctly, and not simply crashes, but produces some wrong results in some obscure cases, so you really need some domain-specific knowledge on to debug this. What kind of agreement you had? Who owns this? And second question, so suppose some component owners investigated these cases. Did you have some agreement, formal, informal, on what kind of bug report we should give you? A nice, clean, no more than 10 lines reproducer, or just a proof that this is compiler's fault? Yeah.
Okay,
Thanks.
so I'll take this question because it's mostly about the userland. I think on the kernel side, they handled a lot of both sides of this themselves. On the userland side, like we essentially would move components that we knew that like we were either comfortable moving ourselves early on, and so we started out with the projects that we had the most familiarity with ourselves and the most familiarity with the other teams. And so we would usually try to entice other teams, be like, hey, look, you can try out this new address sanitizer thing and find some other bugs. Wouldn't you like that? And they would say, oh, that's interesting, and be like, all you have to do is help us switch you to Clang, right? And so I think part of it was that. Part of it was focusing on the projects that we had comfort in, projects that were on similar like sub-teams that were like joint with my team or with, well, in the beginning it was me and a few other loose assorted people on all sorts of teams doing this. But they would basically be interested in moving to Clang themselves. And so we would try and convince people like, hey, this is worthwhile, you should do it. And if people had tests, we would actually go and run their tests and do the performance testing for them if they had it. You'd be surprised, or maybe not surprised, that a lot of these things didn't exist 7 years ago, 6 years ago, 5 years ago. Like testing has gotten a lot more rigorous in the recent years, but in the early days we were able to basically be like, here's your subset of tests. We ran it. Everything is fine. And then as we finally got well, now we're going to move faster and start defaulting things to Clang and checking other things, we would just be more aggressive about it and start switching projects over. A lot of times people didn't want to maintain this legacy external code. And so they were happy that we were switching it over to Clang because maybe it found some bugs and we would probably end up fixing it. But we would ask other teams to help too. Like we would file bugs on them and say, hey, look, this looks like your bug. Can we have you come in and look at some aspect of this, sit down with us for a little bit and help us understand what's going on? Or again, we would just blank it off and say local Clang equals false for 3 months, 6 months, whatever, until we actually had time to investigate it further if it was that complicated. So, and as far as bug reports, we just generally worked with teams who were like, here, we'll help you reduce some of this. And some of the teams were awesome and would basically be like, here's a 10-line reproducer for this. And some of the teams would say, here's a giant blob of code, it's broken, please do something about it. And we would say, okay, well, it's going to take a while, but we'll get it, right? And we would work through it. And again, a lot of this work also was helped out by the rest of the community. I can't tell you how many times we asked a partner company to build some part of AOSP when their LLVM team, like the partner company that was working on Android, would be using GCC to build everything, and they didn't care about shipping their product with Clang. And their compiler team might also look at Clang, but they weren't building Clang for Android. They were building Clang for other things, for GPU compilers or whatever. And so when we would ask them, hey, could you please take a look at this? They would say, well, that's really hard because we don't really work in Android. So we had to bridge those gaps a little bit and say, well, let's make it easier for them to work in Android or work in upstream and reproduce this bug. And so it's sort of both sides would do their share.
Thank you.
Thanks.
Yeah, so I was just a little curious, what were some of your motivations for switching the compiler from GCC to Clang?
So for the user space, we basically were at the point where GCC maintenance was sort of diminishing at Google and in general, and we saw this uptick in Clang usage. And we ourselves were using Clang for things on the device, and we said, hey, we're building expertise here, and yet we're not sort of growing our expertise in GCC anymore. And then there was a couple things that sort of were very different in that era where GCC was behind on sanitizers and other work, and we saw it as a chance to add some extra value, right, security-wise. And we said, hey, look, we want this, right? This is something that's worthwhile doing, even if we don't ship it. And so we started with that and just grew it, right? And then eventually it was like, look, the rest of the world is moving towards LLVM, right? A lot of people are very, very deeply interested in this because of ease of use, ease of, like friendliness of licensing, other things. And they wanted to be involved and said, why are we not taking advantage of that, right? Why not do more? And at that point, it was just obvious what to do, so.
Yeah, and on the kernel side, it was because we came to it a little bit later. By that time, it was clear that for userspace, LLVM was the way forward. And basically, we had people coming to kernel teams saying, you're the last major dependency on why we have to maintain cross-compilers for GCC. What can you do about this? And honestly, the first couple times I said probably nothing. And then again, once we got to 2016, I'm like, oh, this looks like something we could actually do. So that's basically why we switched over. But there have been certainly important other benefits. Our sanitizers team is very happy that you can build a kernel with Clang because now they don't have to take like TSAN and re-implement it on top of GCC. They can just use Clang.
And I think there's a lot of static analysis tools that I was trying to build around. We have a fair amount of out-of-tree code in our kernels on a device that we ship. And the Linux kernel doesn't make it easy for third-party contributors to do things correctly. So I've been kind of looking at using LLVM for static analysis to help find conventions that are used throughout the Linux kernel that, when not followed, are problematic.
Okay, thanks.
Hi.
Hey.
So the Linux kernel is the poster child for memory order consume, which it seems like you've boldly assumed just works. What have you done to stress test RCU, for instance?
So there are actually RCU stress tests in the Linux kernel. I don't recall in what form they're in, but I know that I have seen them before. And as part of normal kernel testing, we run, for instance, the kernel's built-in self-test modules, at least the ones that apply to our kernel. And we're also using more and more of what's called LTP, the Linux Test Project. Again, not everything applies to Android, but we run as much as possible. I think other than the testing, the best way to shake those bugs out is that you ship the dog fooders. And you run these things under your normal user space stress tests. And if there are kernel bugs there, they should manifest.
So you don't have a specific burn-in policy in place where you are actively every day banging on RCU trying to get it to glitch?
I think if there's additional tests that you recommend, let's talk afterwards, and we're more than happy to implement them and make sure that they look good.
All right.
Thanks.
Hello, thank you for amazing presentation. In ARM, we are really concerned about functional safety of our compiler. So I saw one of the reasons to its support of another compiler is for security and safety benefits. And you found a lot of bugs. How quick have the bugs been fixed?
So it depends. In the early days, some of these things we punted for long times because it was deep compiler bugs where we were like, we don't have the expertise to do this. And we don't have the buy-in from the people who do know how to do this. And it was sort of a learning experience for myself and other people in the earlier days. But as time went on, we got a lot more effective in getting help, right? Again, it's the build your network, and people will actually want to do this and be involved. So I think these days we're pretty rapid about being able to get things fixed. Deployment is a lot harder now for toolchain. Now with the userland using it, with the kernel using it, the amount of testing we have to do to say this compiler is ready to go is quite a bit, and it's not as automated as we would like it to be, mostly because of the diversity of mobile devices and having to support all these different products and flaky USB and everything else adds up and slows you down, as opposed to saying, testing something in a data center and saying, we can just run it on a whole bunch of machines and hope that, they'll shake out the bugs. But we do rely on our other teams at Google for doing that. So one of and this isn't in the slides, but, or not as obvious in the slides, but there are other teams at Google who work on Clang as well, right? And they work on it for the data center, they work on it for other devices, other products. And we rely on like the data center team heavily because we actually, when they pick a build and they roll along with top of tree just like we do, when they pick a build and stabilize it and say, this one seems pretty good, we pay attention to those, and then the next one we snap to is usually one of those because we know, at least for the data center use case of x86-64, right, that Clang is mostly like it's a good starting point, and we don't have to sort of do the guesswork of, is this even a good starting point? And then we rely on other teams like Chrome OS team and a few others to actually say, oh, hey, we've tested this too for our things, like, you know, and we sort of collaborate. And so maybe Android gets there first, maybe Chrome OS gets there first, maybe another team gets there first, but we always sort of follow the larger teams who can do better automated testing first, and then, you know, deal with it ourselves.
And another question related to this. I think a lot of people involved into LLVM development can be interested in accessing to this information and in bugs related to safety and security. What do you think the current level of communication in the LLVM community, is it sufficient for this? Maybe we need to separate mailing list, LLVM dev security or something like this to notify quickly about problems and create internal bug reports or reproducers, or start thinking about this.
Yeah, I think that there is, that is one of the scarier things for us, was that, you know, like if there is a critical bug in LLVM and we don't notice it on the mailing list and we ship a new release and just didn't catch it, that, hey, everyone reverted this patch. And we've actually done this, right? We've messed this up before. And so it is kind of hard, but in more recent years, like we've definitely seen that become easier to do, because when things are wrong, they get reverted very, very quickly. People are very good about finding and fixing bugs. And if there is something that's really major, we generally hear it from the related teams. It might be good to have something that's more high alert, like, hey, LLVM, like, you know, like super low usage, hopefully, but high priority, like, hey, if you've, you know, used this particular sync to this build, your compiler may be broken in this very, very subtle way, and that's not a good thing. Maybe giving more visibility to that would be a good thing.
Thank you.
Welcome.
All right, with that, thank you, everyone. We appreciate it.